So we're getting close to the end of chapter 3 now, which is going to finish up with a nice application section where we deal with problems that typically arise in real life scenarios. But before we are going to be ready to do that, we need to discuss a concept called implicit differentiation, and that's what this section is about. Now this is a technique that is applied to an object called an implicit function. But before I can really tell you what those are, I first need to clarify what I mean by an explicit function. And really, just implicit functions are going to be functions which are not explicit. So what is an explicit function? Well, explicit functions are the functions that you're used to dealing with, right? So every function you've ever seen in this course, and likely every function that you've seen in high school, right all the way back to the first day when you first were introduced to the idea of a function, those are all called explicit functions. You plug in an input value, and they give you back output values which are entirely and uniquely determined by the input. So the way I've worded it here is that I say that explicit functions may be expressed as an output which is dependent on a single input variable. So a couple of examples, right? You might see something like, well, you've seen lots of functions like this before, right? F of x is equal to x squared plus 1, right? Or if I wanted to write y as a function of x, I could write something like y is equal to sine of 2x, for example. So those are both examples of explicit functions, because if you plug in an input variable, you'll get an output which is uniquely determined based on the input. So for example, how does this function work? Well, you plug in an x value, it squares it, adds 1, and then sends it right back to you. What about this one? You plug in an x value, what does this function do? It multiplies it by 2, plugs it into sine, records the result in the variable y, and then sends that back to you as output. So those are explicit functions. And I know I'm being repetitive here, but if you glazed over on everything I just said, the most important thing is that with explicit functions, you have an output variable which is dependent only on a single input variable. That's really what it comes down to. And you might want to also take note, particularly of the second example, because this is the example that we're going to be generalizing. This is the notation we're going to kind of use when we talk about implicit functions. And notice the key feature here is the way it's written. It's written in the form y equals, and then everything on the right-hand side of this equation is dependent only on the input variable, which happens to be x in this case. Okay, but an implicit function cannot be expressed in this way. So that's what we're going to fill in here, an implicit function. Cannot be expressed in this way, but is instead called, sometimes you can call them multi-valued functions, but that's not technically correct, but it gives you a really nice way to think about them, and here's what it is. Really, remember with explicit functions, you plug in a value, and that uniquely determines an output value which gets sent right back to you. But with implicit functions, you might plug in one particular value, and then there's several possibilities for values that could come back to you, right? So that's why they're sometimes thought of as multi-valued functions. So the output is not uniquely and completely determined simply by just an input value. There's something else involved as well. Maybe it's a random chance, or maybe it's choice somehow, but that's the big difference. If you plug in an input value, there's several possibilities for output values. And when you write them down, when you write down implicit functions, their key feature is that they cannot be written down like this one is. You can't write it as y equals and then only have x's appearing on the right-hand side of the equation. Like for example, this one doesn't have any appearance of y on the right-hand side. But if I said plus the square root of y or something like that, that would make it an implicit function. Okay, so really what this last part of this line here where it says they may be expressed as a relationship between two variables, that's really all implicit functions are. They're relationships between two variables. Okay, so that's about as much as we can say without actually getting into an example. But one last thing that's I've written down here, I'll just mention it. You can still graph them though. You can still graph these relationships, but in general they'll fail the vertical line test, which is why they actually fail to be explicit functions. Okay, it's best to just go to an example now, because there's not much more. You will get no clearer just by talking about them. I have to actually show you. So consider the graph of the equation x squared plus y squared is equal to 1. This is an example of an implicit function, right? This is, let me actually mention that. So this is an implicit function. You can try as hard as you like, but you'll never be able to write this as simply just y equals, right? You could solve for y squared, right? But you'd never be able to solve for y entirely without throwing away some of the information. But let's go to the graph. What's the graph of this equation look like? Well, this is actually a circle. It's the equation of a circle with the center at the origin and radius 1. So if you were to graph this equation, that's what you'd get. So let's draw a sketch of that circle. So there's the point 1 on the x-axis. Go up like that, come around. And that's what we're dealing with. We're dealing with the unit circle. This would be the point 1 up there. All right, so what do I mean by failing the vertical line test? Well, exactly what you'd think, right? If you draw a vertical line right here, you can see that it intersects the curve at 2 points. It intersects the curve here and here. So because of that reason, this graph fails the vertical line test. So let's say the vertical line test is failed. So this is not an explicit function. Okay, but something else that you might notice about this graph is that it's still smooth, right? There's no kinks or corners or sharp bends. So what does that mean? That means you can draw tangent lines, right? Let's look at an example. Let me actually pick a particular point on this circle, the one that has x and y coordinates both equal to 1 over the square root of 2. Let's say that's what this point is. And you can check that this is actually a point on the graph of this equation, because if you plug 1 over root 2 in for x, then x squared is just 1/2. And then same with the y. If you plug in 1 over root 2 for y, then y squared is 1/2. So you get 1/2 plus 1/2, and of course that equals 1. So this point does satisfy that equation. So that's actually a point on the graph. Let's sketch the tangent line to the circle at that point. You're going to get something like this, right? That you can see that there is a tangent line that at least exists abstractly, but if you can draw it, then you should be able to write down its equation, right? But in order to write down the equation of the tangent line, you need to, first of all, you need the slope, right? We already have a point that line goes through. It goes through the point 1 over root 2, 1 over root 2. So if we had the slope of this line, then we can get the equation. Now you might guess, it looks like the slope is roughly -1, right? Because it seems like it's going down and to the right at roughly a 45-degree angle, so it's probably you're expecting to get a slope of something like -1. But how would you actually calculate that slope? How would you actually show that that slope is any particular value? And that's where implicit differentiation comes in. Okay, and that's the technique I'm going to illustrate to you right now. But the point of this little drawing here was to illustrate that while the graph does fail the vertical line test, it's still smooth. You can still draw tangent lines, and for that reason, we're gonna try to get our hands on the equations. So here's how you can find the slope of this tangent line. So this is a technique called implicit differentiation. Okay, so here's how you start. You start with the equation. We've got x squared plus y squared is equal to 1. So what are we going to do? We're going to differentiate both sides of that equation with respect to x. So we're still going to think of x as the variable here, the input variable, and we're still going to think of y as the output variable. So you're still going to think of y as a function of x, but it's going to be y is an implicit function of x in this case, because it fails the vertical line test. Okay, so what's the logic here? Well, the idea is if y is an implicit function of x, then the left-hand side of this equation is also a function of x, and in the implicit sense, right? X squared is dependent on x, and y squared is dependent on x, so the entire expression is dependent on x. Now the right-hand side is also a function of x. It's a constant function of x, but it's still a function of x. So the idea is if you have two functions that are equal, which is really how you should interpret this equation, well, then their derivatives must also be equal. If you differentiate both the left and the right-hand side with respect to x, then you should get the same thing. That's the logic we're employing here. But then now, how are we going to calculate these derivatives? Well, we're just going to use all the properties of derivatives, along with the chain rule, the sum rule, product rule, addition and subtraction, quotient rule. Use every rule at our disposal, and that's really what it comes down to. And just carefully follow these rules. So I've got x squared and y squared. Both of those are added together. Well, how do derivatives behave when you plug in sums of functions? Well, the derivatives just split up nicely. You just take the derivative of each one separately. So if I take the derivative of x squared, well, that's just a power of x. We're going to handle that in the ordinary way. Apply the power rule to get 2x. What about y squared? How do you differentiate the y squared term? Well, that's where things change a bit, because this is the derivative. If it was the derivative with respect to y of y squared, then we would just use the power rule and say 2y. But it's the derivative with respect to x here. And y is not the same as x, right? Y is, in fact, it's a function of x. It's an implicit function of x. So what do you do when you have an inside function? The answer is you use the chain rule. So I'm going to draw the bubble like I have in the past, just to remind you of what it feels like to think about the chain rule when you have an inside function, right? We first differentiate the outside function and leave the inside function alone. What do we have? We have the inside function squared, or y squared. So the derivative of the outside function, if we left the inside function alone, would be 2y. That's the first part of the chain rule, right? But then the rest of the chain rule says we also have to multiply by the derivative of what's inside. We have to multiply by the derivative of y. And you might say, well, we don't know the derivative of y, right? The whole point of this is that we want to figure out what the implicit derivative of y is, or figure out what derivative we're going to get for y using this implicit differentiation technique. So we don't actually know what the derivative of y is. We don't know what y prime is, so to speak. Well, why don't we just write it down symbolically? We'll just write y prime. Right? That kind of avoids the issue, but yet we still wrote down the derivative of the inside function, so we're not liars. And that technically is the derivative of y squared. It's 2y times the derivative of y. We just don't know exactly what it is yet, but that's okay. But that gives us enough that we can keep going now. So that's the left-hand side. Now the right-hand side, this is a little easier because 1's a constant. Derivative of any constant is 0. Okay, so now what you have is you have an equation that gives you a relationship between y prime, y, and x. And the idea is just solve for y prime. So subtract 2x from both sides, and you get 2y, y prime is equal to negative 2x. Then you can divide both sides by 2y, and you'll get y prime is negative 2x over 2y. And you might as well cancel the 2's and write this as negative x over y. So let's put this in just as a little summary here. We'll say y prime is equal to negative x over y. And I'm going to circle this just in green because this is not really, nothing was asked for in this example. We're just exploring here a bit, but this is a key result that kind of follows from this work. So this, if I were to draw a box around this, this is what implicit differentiation looks like. Okay, you start by writing down the equation that defines your implicit function. You take the derivative of both sides with respect to your input variable, which in this case is x, and then you just follow the rule. And the chain rule is going to come in all the time. Differentiate each side and just pay very close attention to whenever you have y as an inside function. And then just use the chain rule whenever that happens, like we did with this term. Once you get to this part, all the derivatives are taken. Just isolate y prime. Isolate the derivative that you're looking for. And that's what we get down here. Y prime was equal to negative x over y, and that's what we summarized down here. Now, I want to mention one other thing before we go any further. Note that y prime is not just dependent on x anymore. It's dependent on two things. It's dependent on x, which is what the input value was for the original function, but it's also dependent on y. So that is a new thing. We're not used to that. Usually our derivatives are only dependent on the input value for the original function. But since if you can't express the original function explicitly in terms of x only, there's no reason to expect that you'll be able to do that for the derivative. So that's perfectly reasonable at this point. Okay, so, well, how are we going to use this now to get the slope of this tangent line? Well, we have a point on the graph that this line is supposed to be tangent to the curve at. So the idea is the slope of this tangent line is going to depend on two things. It's going to depend on the x-coordinate of the point and the y-coordinate of the point. It's no longer enough to plug in simply the x-coordinate, right? In the past, we've always just plugged in x-coordinates, but this time that won't be enough. Because if you try to just plug in the x-coordinate here, like x equals 1 over the square root of 2, the derivative is going to say, okay, well, there's 2 points on the graph with an x-coordinate of 1 over root 2. There's this point, but there's also another point down here that has an x-coordinate of 1 over root 2. So that's why you also have to specify a y value. That's why this y is showing up as well. Now, if I specify 1 over root 2 for x and then 1 over root 2 for y, then that's me saying, hey, I'm talking about this point, not this point down here. Because this would have a different tangent line, right? There'd be a tangent line up here that has a slope that's different than this tangent line. So that's why we have to plug in both an x value and a y value. So let's do that. What do you get when we plug in 1 over root 2 for x and 1 over root 2 for y? So let me just separate the work. So our slope is going to be what? Well, it'll be, I'll plug 1 over root 2 for x, so we get negative 1 over root 2 over 1 over root 2. And you can carefully divide the fractions if you want, or you just have a numerator and denominator that are the same. You can cancel them out and just think of it that way. You'll be left with a negative 1. And we said that right at the beginning. It looks like the line has a slope of roughly negative 1 because it seems to be going down 1 over 1, down 1 over 1. It's going down at roughly a 45-degree angle, so that's no surprise that we got a slope of negative 1. But this is how you can use the implicit derivative to calculate that. So, well, here we got our slope. What's the rest? Well, we got the point that the line goes through. We can just write the tangent line's equation down now. So the tangent line is just given by the equation y minus y naught, which is 1 over root 2, is equal to the slope, which is negative 1, times x minus x naught. And x naught was 1 over root 2 as well. So this is your equation of the tangent line. And I'm circulating in green instead of red just because red is reserved for the solutions to actual examples where we were asked for something. But we weren't really asked for anything here. This was just exploratory. But if you were asked to find the equation of a tangent line to the graph of an implicit function, this is the technique that you would use, right? It's the same idea. Find the derivative, plug in the point to get the slope. Once you have the slope, use point-slope form to get the equation of the line. So nothing changed except the manner in which we take derivatives.